This is Dr. S.P. Harsa from Mechanical and Engineering Department, IT Roorkee. I am going to deliver my lecture 31 on the course of the strength of materials, and this course is developed under the NPTEL program, National Programs on Technology Enhanced Learning. Prior to start this lecture, I would like to refresh those prior concepts which we discussed in the previous lecture. In the previous lecture, you see, first we discussed about the main the formula which we derived for the simple bending stresses and the shearing stresses when it is under the the loading condition of point load or U.d.l or whatever like that with the simply supported beam. So that numerical problem which we discussed, and we also found the principal stresses for those things when a beam is subjected by the bending as well as the shearing stresses, how we can calculate the principal stresses, and then how we can calculate the principal planes also. So this problem which we discussed with the numerical problem, and then we discussed the real feasible problem that if we have the composite beam, because right now you see in the recent time you will find that mainly it's a some fibers and we have the different kind of the composites are there. So because they provide the different kind of unique properties in the kind of beams, so we are not going for the conventional beam design, we are always going for the composite beam. So but you see, if you want to analyze the composite beam, then it is not exactly as straight as the normal beam is, because in that we have two different kind of materials and we need to check it out that actually how the fibers are reacting each other when a composite is there. So even from the scientific point of view or from the research point of view, again we have to be very careful about the the compatibility of these two different kind of materials, that just we discussed about that if we have a wooden plate, two wooden plates, and in between if we have a steel plate, then how we can analyze. So if you go for the basics, then we discussed that you see it is not a valid thing just to apply straight way the same bending theories in that, because you see in that in the general bending theory or the shearing part in these beams, we found that we have a different these Young's moduluses are there and we have a homogeneous material, but here you see it is not the same. So for that, what we need to do here, we found that there is an alternate way is there, that just replace the middle portion or the different material portion by an equivalent section based on their theories, like the stresses with the thickness or the Young's moduluses with the thickness. So we found that if they are valid, means you see if the ratio of their thickness is exactly equal to the reciprocal ratios of their these Young's moduluses, or we can say that if they are going up to the elastic deformation, then the stress into thickness is equals to, in the one section it is equals to the stress into thickness into the another section, then we can say that yeah, these theories are applicable. Then you see we observed that if we put the equivalent section, then sometimes the equivalent section is much larger than the previous section based on their Young's moduluses ratio. Or you see if like in the other case which we discussed, that if we have the two steel section and in between the concrete section is there, that means you see the two different ductile material and in between there is a brittle material, obviously it has a less Young's modulus of elasticity property, then it is a small portion is there. So how the fibers are just lined up, or how the streamlines are there of the settlement of these fibers, which is very important. So all this discussion which we made up in the composite beam in the previous section, and then you see in the last section we discussed about the deflection part, that actually if a beam is under the deflection, then what you see which of the theories are applicable. Then you see we put certain assumptions in those things, that actually if the deflections are there, then again you see it has to follow the Hooke's law, means the elastic deflections are there, and you see if you want to measure the deflection, this x axis is going along with the longitudinal axis, because, or we can say the horizontal, the fibers are there, and the y axis which is always measuring the deflection, and then we described how the deflections are coming in those things. And then again another assumption was very important, that you see whatever the curvature path is coming in due to the deflection is it has to be very small in order to ensure that yeah, this is the elastic region is there within those component. So with those certain assumptions, you see we found that, and then a third assumption was very important, that the shearing is to be neglected. So whatever the deflection is coming or the deformation is coming due to the shearing action, it has to be neglected because they are coming in a very small way. But if you are minutely observe those things, then we found that it is very complicated to analyze those things along with the bending part. So it has to be neglected. So these three assumptions we made for the deflection, and with those assumptions we concluded that actually the bending moment is equals to E into I. E is the Young's modulus of elasticity, I is the mass moment of inertia, into like d2y by dx square. So with that theory, now again in this lecture we would like to continue the same deflection theory, and then you see we will see that if we have a different combination of the beam, then how we can analyze those things with that particular way, the method of analysis. So here you see like again with the same equation we have this m is equals to EI into dy by d2y by dx square. So now if I am differentiating the basic equation of the deflection, then we have dm by dx is equals to E into I d cube y by dx square. So if you know that we have the basic relation between the bending moment and the shear force, F is equals to dm by dx. So here if I am replacing this shear force by dm by dx, then we have F is equals to E into I d cube by dx cube. So above expression represent the shear force, whereas you see the rate of intensity of loading can also be found out by differentiating the expression of the shear force. So if you remember what we have df by dx is nothing but equals to the rate of loading q or w, whatever you see. So you see here by again differentiating this f by df by dx, you will have the rate of loading. So the rate of loading is nothing but equals to minus df by dx, or we have w is equals to minus E into I d4y by dx4. So concluding those things, what we have first of all the slope I is equals to dy by dx. So you see if a beam is under any kind of loading, we can get easily the slope by simply differentiating their domains x and y. So dy by dx will give you the slope, that at what slope the deflection is occurs, and then you see once you have the slope, then by simply like the bending moment can be easily calculated, which is equals to E into I, which is the flexural rigidity. There is a very good term in that. So bending moment is equals to E into I d2y by dx square, and then corresponding shear forces are nothing but equals to E into I d cube y by dx cube, and then the like the rate of loading or the load distribution can be easily calculated, which is equals to E into I d4 y by dx4. So now you see we have like all those things, but one has to be very careful to check it out that how one can get easily the bending moment, shear force, rate of loading or slope with those derivative component, with the single, second derivative, third derivative or the fourth derivative. So with those component, now you see we just want to find out the deflection. So there are various methods available for that. So the deflection of loaded beam can be easily obtained by using various methods, and one of the method for finding out the deflection of the beam is direct integration method. That is the method using differential equation, which like we have derived previously, that for the slope, for the bending moment, for the shear force and for the rate of loading, we found that only the differential equations are there. So if we put the integration method, straight away you can get all those values which we are looking for. So first method is pretty common method, very standard method is the direct integration method with the using of those governing equations. So you see here the first basic equation for the deflection which we derived is m is equals to E into I d2y by dx square. So now by keeping m divided by EI will give you d2y by dx square. So now you see here what we have d2y by dx square is equals to m divided by EI. By keeping integration, because you see it's a direct integration method, so if you put the integration, what we have dy by dx is equals to integration m divided by EI into dx plus a. So this equation gives you the slope of that, because dy by dx is the slope of a loaded beam. And then again if we put the integration here, then we have y which is equals to double integration of m by EI into dx plus ax plus b. So in the deflection formula we have the double integration of this m by I into dx, and we have the two main the constants a and b, which are the constants of integration to be evaluated from the known conditions of the slope, that what kind of beam which we are taking and what kind of loading conditions are there for that, and the deflection for a particular value of x. So with that you see now we would like to first of all go for a different kind of combination, that if you have a cantilever beam with this point load at the center, or if we have the cantilever beam with the U.d.l, then how we can configure those things. So, the first example, let us consider the few illustrative examples to have a familiarity, with the direct integration method. So, the like the different cases which we are going to discuss here. The first case is we have a cantilever beam with the concentrated load at the end. That means, you see, we have a one free end, we have one fixed end. So, at the free end now we are keeping one like the point load or concentrated load at the extreme end, and a cantilever beam is subjected to a concentrated load W. You can see on this particular figure at the free end, it is like required to determine the deflection edge of this particular beam. So, here you see this is the free end, and this is the this is the fixed end, this is the free end, and if you are like going with the particular longitudinal way, then we have x equals to 0 and x equals to L. So, the total length of the beam is L, and you see here this free end is subjected by the radial load W, which is going towards the downward direction. So, now when we keep those things here, we have a kind of deflection of this shape. You just focus on this thing here, this is the maximum deflection going like this, and at this particular end we have a 0 deflection. So, now we would like to find it out that how much deflection is there of the beam when it is like subjected under the radial load of like at the extreme corner of the free end. So, now we are taking the x section at some portion which has a distance of x from a free end. So, with that consideration, now just take the cross section of the beam which is like loaded at xx section from the distance like x from the left hand corner, or we can say that like this is the reference point for this, and just we need to write down the expressions for the shear force and the bending moment of those things. So, first of all, the shear force, since it is going at the extreme corner, it is going in this direction, and at this particular right section it is going in the upward direction. So, we have a negative like as per the sign convention of the shear forces, it is the negative one. So, shear force is at xx section is nothing but equals to minus W, or the bending moment, since it is going in the downward, the hogging one just in the downward direction. So, it is again you see the negative directions are there as per the sign convention of the bending moment. So, bending moment at xx section is minus W into x. So, therefore, you see the bending moment is nothing but equals to minus W into x for the xx section. Go for the first equation, which is m by EI is equals to d2y by dx square. So, with that, you see if you are keeping this m which is equals to minus W into x, we have d2y by dx square is equals to minus W into x divided by EI. So, now you see what we have. Now, we have the equation for the generalized condition of the cantilever beam which is loaded by point load W. So, W d2y by dx square is nothing but equals to minus W into x, because we are just going with the x action. So, minus W into x divided by E into I. Now, if we integrate, so integration will give you like dy by dx, that means the slope is equals to minus W integration of the W into x divided by EI into dx. So, since we are going with the integration of with the x, so we have minus W x square divided by 2 EI, because x integration will give you x square by 2. So, we have dy by dx is equals to minus W x square divided by 2 EI plus a constant A. Again, you see we are integrating to get the value of the deflection. So, integration dy by dx is nothing but equals to integration of minus W x square by 2 EI plus A into dx. So, now you see we have the generalized like the deflection equation for a cantilever beam which is loaded at the extreme free end corner by radial load, or we can say a concentrated load W, which is equals to y equals to minus W x cube by 6 EI plus Ax plus B. So, this is a generalized condition, generalized equation. After putting the lots of constraints one, or we can say the different the boundary values, we can get exactly that actually what we want for a generalized beam. Okay. So, now you see with those A and B constants can be easily evaluated with the using of boundary condition, as I told you. So, here you see what we have, it is a cantilever beam at x equals to L, that means you see the fixed end, there is no deflection, as I told you, because it is a free at free end we have the main deflection, at the extreme corner of this there is no deflection. So, at x equals to L, y equals to 0. So, this is the first condition, and the second condition you see at x equals to L, that means you see the fixed condition, there is no slope. So, no slope, no deflection condition at the rigid end. So, you see at x equals to end, we can again keep both the condition to get the value of this A and B. So, you see here if you are keeping that in the slope equation dy by dx, where at x equals to L the y equals the dy by dx equals to 0, and in the deflection condition x equals to L, y equals to 0, if we are keeping those things, we can get the values of A and B. So, here you see here when we are keeping in this like the slope condition dy by dx, which gives you a value. So you see, if you are keeping those value like 0, then we have a equals to wl square divided by 2 ei. So you see here, it's pretty simple that now we have like these a condition is there. So if you are keeping those like a value in that, we have the y equals to like this minus wl square by 6 ei plus a into l plus b, because we are keeping x equals to l here. So now like we have the b value, because the slope is 0 at this particular condition where x equals to l. So if you are keeping those, then we have this b is equals to wl cube divided by 6 into ei minus a into l, and now since a is there already, w like wl square divided by 2 ei. By keeping those values, what we have wl cube by 6 ei minus wl cube by 2 ei. So by concluding those things, we have the b value which is minus wl cube by 3 ei. So now you have the value of a, which is wl cube wl square by 2 ei, and you have the value of b, which is wl cube by 3 ei. So by keeping those values here, we have the final generalized equation for like a cantilever beam in terms of the entire beam. Earlier you see we have an equation in terms of the x axis. Now we have for entire length of beam, that is capital L. So y equals to 1 by ei wx cube by 6 ei plus wl square by 2 ei into x minus wl cube by 3 ei. So you see the slope also like one can easily calculate the slope for that one also, as the deflection would be like the maximum at the free end, and hence you see if we are keeping x equals to 0, because like we are keeping we are simply putting the this radial load at the free end. So obviously you see it will give you the maximum slope at the x equals to 0, because the slope at rigid end is 0, the slope is maximum at the free end. So by keeping x equals to 0, one can get easily the maximum slope, or we can say the maximum deflection. So y maximum is nothing but equals to like if you are keeping x equals to 0, you have minus wl cube by 3i, which is like a good value. That means you see now if we have the radial load is there at the free end, we can easily get the maximum deflection at the free end just by knowing the w means what, how much like what is the amount of these things are there, and then l cube. So if you have like the longer beam, a cantilever beam, again you see here the conditions are the cantilever beam, obviously more and more deflection are there. And if you have a very small beam, you see it has, you see after a certain like distance we have the rigid end, obviously you see the whatever the like the resistance is coming is always maximum. So you see the y maximum, that means the deflection maximum is always like one can get by putting more amount of load, one thing, by like choosing the more length of beam, so that you see we have like the more deflection, but it has the reciprocal relation with the E and I. Means you see if you have more like the Young's modulus is there, that means if the more stiffened properties are there, definitely you see the less deflections are coming, and you see the moment of inertia also, that what kind of cross section you are using, corresponding changes are there in the deflection terms. So these are the influencing parameters for calculating the maximum deflection. So again you see the maximum deflection is nothing but equals to minus wl cube by 3 ei, or also we can calculate the slope maximum, which is nothing but equals to wl square by 2 ei. So you see here one can easily get those values by keeping the value x equals to 0, because we know that the slope and the deflection, they are maximum at the initial point where the cantilever is there, the free end is there, the slope and deflection at 0 at extremely like those rigid point where you see the rigid bonding is there in between the beam as well as the support. So now you see this was like the case where the free end like is the free end is like experienced by a point load. Now you see the case 2, again you see we are going for a cantilever which is like experiencing by a uniformly distributed load. So now you see here, you can see on your screen the figure, we have like the U.d.l is there all across the entire span of the beam, and then it is supported by one end. So in this case, a cantilever beam is subjected by U.d.l, which has the rate of intensity like of the loading W per unit length, and the same procedure again we need to adopt for that. Again at x equals to 0, you see these like the conditions are there, at x equals to L these conditions are there. So again we have to be very careful that at x equals to 0 the beginning point, and at x equals to L the end point, how the conditions are varying, and then you see like the total entire length is L. Again we need to cut the section at xx which has a distance of of x from the left hand portion. So by taking those things again, you see from this UDL, the loading condition is coming towards the downward direction, and you see at the support, which is exactly at the extreme corner of right, the support reactions is coming on the top of direction. So with this direction again the shear force is negative, and it is coming in this the hogging portion. So again the bending moment is also the negative as per the sign convention of shear force and the bending moment. So with that, shear force is equals to minus W, bending moment is equals to minus W into x, that is the load, into x by 2, which is the pointing is there. So we have minus W into x square by 2. By keeping those values in the basic equation of the deflection, that is m by ei equals to d2y by dx square, we have d2y by dx square is equals to minus bending moment is wx square by 2, so minus wx square by 2 into ei. So again you see again the same procedure which we followed for the point load here. For the UDL also we have the slope dy by dx is nothing but equals to minus wx cube by 6ei, because the square term is there. So x cube by x cube by 3 will come, and since already 2 is there in the denominator side, so we have minus wx cube by 6ei plus a. So now you see this is the one equation for the slope condition, dy by dx is equals to minus wx cube by 6ei plus a. Again by integrating we have the slope deflection equation. So you see the integration dy by dx will give you integration minus wx cube by 6ei into dx plus a times of dx. So obviously we have the two integrating coefficients a and b here. So the final equation for a cantilever which is experiencing by a load of UDL over the entire span of the beam, and this cantilever beam is we have the free end and we have a rigid end. So for that the deflection formula y equals to minus wx4 by 24 ei plus ax plus b. So now you see again we need to follow the same condition here, the slope and the deflection at the rigid point, that means at x equals to L, which is always b equals to 0. So now you see here the slope equation which we have wx cube minus wx cube by 6ei plus a. If you are keeping at x equals to L, the value of a will be coming, and you see we have the deflection term, that is minus wx4 by 24 ei plus ax plus b. So if you are keeping y equals to at x equals to L, this the dy by dx is also coming 0 and y equals to 0 will come. So for those conditions we can get the value of a and b correspondingly. So you see here we have for the slope condition where dy by dx is equals to 0 at x equals to L. If we keep those things here, then we have the value of a which is equals to wx cube by 6 ei. So now you have the value of a. By keeping the x equals to L, y equals to 0, by keeping those values in the deflection curve, then we have the value of b which is equals to WL4 by 24 ei minus WL4 by 6 ei from this a term. Okay, so because we are keeping x equals to L, so you see here it will come as WL4. So now you see b value will be minus WL4 by 8 ei. So now you have the value of a, that is wx square by 6 ei. You have the value of b, that is minus WL4 by this 8 ei. By keeping those values in the main equation of the slope, you have y equals to 1 by ei inside bracket minus wx4 by 24 plus WL cube x by 6 plus minus WL4 by 8. So now this is a generalized equation for a cantilever beam which is loaded by this UDL, which has the intensity of load is W, and you see the total length of the beam is L. So for that you see we have the deflection term is this, and as we know that the maximum deflection and the maximum slope is always occurs at the free end where x equals to 0. So if we keep that value at x equals to 0, we have the maximum deflection is y maximum is equals to minus WL4 by 8 ei, and we can also get the maximum slope where the x equals to 0, that means the beginning point is there, which is also equals to WL cube by 6 ei. So you see here for these cases also we can easily evaluate it, that what will be the value, the maximum and minimum values are there of the slope as well as the deflection for the cantilever beam when it is subjected by point load in the case 1 and when it is subjected by a cantilever this UDL in the case 2. So now you see these two cases were discussed for the simple cases of the cantilever. So now you see the third case, if we now simply change the the simply supported beam. So by taking a simply supported beam here, the boundary conditions are altogether different. So you see here just in the the diagram in front of you, you have a simply supported beam with the uniformly distributed load, and in such a case simply supported beam is subjected to a UDL whose rate of intensity is W per unit length. So you see here we have like the total length is L and the intensity of this is W per unit length, and you see the UDL is all across, spread it out over the entire span of the beam, and then you see we have the simply like these supporting points are there, so the reactions are coming all the way from these points. So now if we are replacing those things, since like the UDL is symmetrically distributed, so at the reactions are always be equal and they are coming from W by 2. So you see we have W into L. So this is, you see, like the W, this is like the intensity is there. So if you multiply with the L, we have the total load. So WL by 2 will be the reaction at this end, WL by 2 will the reaction at this end, and they are coming throughout the load W into L. And since because the intensity is the W is there and the length is the L, so the total load is coming by the multiplication of these two. In order to write down the expression for the bending moment, consider any under any like the cross section at the distance of x. Again we need to go with the same procedure which we followed for the cantilever beam. Cut the section by xx which has the distance from one end at the x. So you see here this reaction forces are WL by 2, and from this x distance we are just like our focused here for this kind of sections is this one xx. So for these kind of sections again we need to calculate the shear forces and the bending moment for these things, but here the sign conventions are different, because you see here the reactions from the simply supported beam at this extreme left corner is going in the top direction, and the loading due to this UDL is coming in the downward direction. So for these kind of sign convention we have the positive like the shear forces. So shear forces at xx section is W into L by 2, because you see like it is coming at the L by 2 minus W into x. So like since it is like the UDL is there, so obviously it is always coming in terms of W into L by 2 minus W into x, because it is an intensity. So now these forces are like that, and then you see we have the bending moment while considering like one end at the fixed end. So you see the bending moment at xx is nothing but equals to WL by 2 into x minus W into x, that is the load, and it is concentrated at x by 2, so W into x by 2. And since you see like due to the simply supported beam, it is again going into the sagging way like that. So again you see it is as per the sign convention it comes as a positive way. So either the shearing forces or the bending moment, they are supposed to be positive as per the sign convention which we have used. So bending moment at xx section is nothing but equals to WL into x divided by 2 minus WX square by 2. So now you see you have the bending moment. Go for the like the basic equation for the deflection, that is m by EI equals to d2y by dx square. So by keeping that value you have dy by dx square is equals to 1 by EI, okay, that is the constant one, and m is nothing but equals to WL into x divided by 2 minus WX square by 2. And now you see you can like by integrating one can easily get the slope equation dy by dx, which is nothing but equals to integration of W into L into x divided by 2EI into dx minus integration of WX square by 2EI into dx plus a. So now we have, you see, since only the variation is the x is there and it is the integration of these things x into dx. So dy by dx is nothing but equals to W into L into x square divided by 4EI minus WX cube by 6EI plus a. So now you see here we have a slope equation for that, and in the slope equation we have one constant term, that is a. Again by integrating we have the deflection equation which carries the two different constants, and one can easily get those constants by putting the boundary conditions. So by integrating again the slope equation we have the deflection y for, you see, a simply supported beam like carries the UDL W intensity, and then you see for that the deflection y is nothing but equals to W into Lx cube by 12 EI, because again by integrating it is x square by 4 is there, so x cube by 3, so x cube into, and since already 4 is there in denominator, so we have WL x cube by 12 EI minus, you see, WL minus W and x cube is there already, so WX4 by 24 EI plus AX plus P. So this is, you see, the first equation which gives you a clear cut description about the deflection, that how it varies with the x. So you see here now as we move like right from x equals to 0 to x equals to L, we have a different boundary conditions. So here boundary conditions which are relevant in this case for a simply supported beam, and the two reaction forces are there at the extreme corner. At x equals to 0 there is no slope, and like at x equals to L, there is no slope. As in the previous case, you see there was the maximum slope is there at the free end, but here you see both ends are equally supported, and like the reactions are also equal for both of the ends. So that's why you see there is no deflection is there at the extreme corners. Only the deflection comes in the middle portion, which will be the maximum part. So here you see, by keeping those things, at x equals to 0 we have y equals to 0. At x equals to L, we have y equals to 0. Now, after applying those things, we have if you just apply in the next equation where x equals to 0, y equals to 0, you see here in all of the term, in the deflection term, you see WLX, W into x and A into x, all those x terms are there. So if you keep x equals to 0, we have B equals to 0. So one coefficient is gone, and then you see by keeping at x equals to L, y equals to 0, we have the value of A, and this value of A is nothing but equals to W minus WL cube by 24 EI. So now you see you have the two coefficients value, B which is 0, A which is minus WL cube by 24 EI. Keeping those values in the main equation first, we have the final term equation for the deflection of a cantilever beam, of a simply supported beam which carries a UDL. So y is the deflection for those kind of conditions, so which is equals to 1 by EI WL x square by 12 minus WX4 by 24 minus WL cube x by 24. So now you see you have a clear cut description that actually if you go with the x right from x to L, then what the variation is there in the deflection as well as the slope. So in this case the maximum deflection will occur at the center of beam, as I told you. So if you are keeping at x equals to L by 2, you have y which is equals to y maximum. That means you see the position where the load is being applied at the middle portion. So if you substitute at x equals to L by 2, we have y equals to y maximum. So y maximum is nothing but equals to 1 by EI. Now you have WL by 12, so x cube is L cube by 8 minus W by 24, x to the power 4 is there, so L4 by 16, because we are keeping at x equals to L by 2, and you see in the final term we have WL cube by 24, and since x is there, so L by 2 is there. So by summing up all those things, we have y maximum at the center point where x equals to L by 2 is there, is nothing but equals to minus 5 times of WL4 by 384 EI, which is a very important formula, that if we have a simply supported beam and it is carrying only a UDL, there is no additional force is there, only a UDL is there which is spreaded all across the span of the beam uniformly, then you see you have the deflection which is maximum value at x equals to L, and the value of this deflection is 5 by 384 WL4 divided by EI. So one can get easily those values, and you see one has to be very one has to be remember this formula, because this formula is very important for calculating the deflection for this kind of thing. So you see here, now we would like to conclude those things. The value of the slope at position where you see the deflection is maximum would be 0. Means you see here, now if you want to calculate the value of slope where you see the deflection is maximum, always it gives you the 0 value. That means you see at the center position where we have the maximum deflection, the slope is 0. The value of the maximum deflection would be at always center, as we discussed here, like these things. So at x equals to L by 2. The final equation which governs the deflection of a loaded beam, just we discussed already, that it is equals to 1 by EI WL x square x cube by 12 minus W x to the power 4 divided by 24 minus WL square L cube into x divided by 24. By succession differentiation, one can find the relation for the slope, bending moment, and the the shear force and the rate of loading, as we discussed in the first section of that how to correlate those things. So here also for a simply supported beam under this UDL, one can easily evaluate those things for these cases. So now you see here again, for different reasons you can go for this here, that we have a simply supported beam, again the same which we discussed, UDL is there. So the deflection term as we discussed here is nothing but equals to y into, now since it was 1 by EI, so multiply this, so y into EI is nothing but equals to WL x cube by 12 minus WX4 by 24 minus WL cube x divided by 24. So this is there. So here you can have a clear feeling that since it is a UDL, okay, and you see at these 2 points there is no the deflection, so deflection is 0 at the 2 extreme corners at x equals to 0 and x equals to L, but the maximum deflection is there at the center position where x equals to L by 2. So you see here, and since the deflection was minus this 5 by 84 WL4 by EI, so you can see here the deflection is going in this way, okay, and here you see since it is just like that, so we have these maximum deflection, and it is the value of this. And then you see if you are going for the slope conditions dy by dx, then it is nothing but equals to ei into dy by dx is nothing but equals to 3w into L x square by 12 minus 4 into wx cube by 24 and minus wl cube by 24. So with those conditions, in the sloping conditions, now you see if you are keeping those values there, then you see here what we have here in this particular situation, the slopes are always, as I told you in the previous section, the slope is always 0 where the maximum deflection is there, and maximum deflection we are getting at x equals to L by 2. So you can see here this is the kind of this convention is there from positive to negative. So at this particular point where the maximum slope is maximum deflection is there, the slope is 0. And since you can see here in these terms what we have, the square into length, this is already cubic and this is cubic. So we have a third degree polynomial, the curvature path is there for this particular slope. So though this slope is very small, but it has the third degree of polynomial in this curvature. So we have at this particular corner we have the minus WL cube by 24 where the x equals to 0, and at x equals to L you see we have plus WL cube by 24. So you see here minus to positive, you see it varies in this particular way, and you see it has a characteristic of the third degree of polynomial, and it always passing from a 0 slope where the maximum deflection is there. So it is exactly these things. And then you see again we can go for the bending moment and the shear forces, which we discussed many times. So you see here again by this differentiating these things, what we have d2y by dx square is nothing but equals to 1 by ei w lx by 2 minus wx square by 2. So you can see that the bending moment variation is exactly similar to the deflection, because at these two extreme corners of the simply supported beam there is no the bending moments are there, but it has a maximum value where you see because of the UDL we already evaluated, and you can see this particular the figure also corresponding to the equations, we have the maximum value of bending moment at the center point, which is equals to WL square by 8. So now you see with those bending moment diagram also you can again visualize that shear forces, which is in this condition it is positive in this region and it is negative in the other region on the right hand direction. So you see with that we have the WL by 2 in the positive region and it is minus WL by 2 in the another region. So it is passing from those things. So again we have a very clear cut reason that you see these equations are almost equal to those conditions. That means you see when it is a simply supported beam is there and it is loaded by a uniformly distributed load, so we can easily evaluate those deflection, where is the maximum deflection is there, where is the minimum deflection is there. With that you see we can calculate the slope conditions, that actually how the slope varies with that kind of a deflection. Then we can also find it out the bending moment as well as the shear force, those things. So shear forces is simply obtaining, as we discussed, that ei into d cube by dy dx cube will give you the f, and which is equals to WL by 2 minus Wx. So now you see again df by dx will give you the rate of loading, we discussed in that. So again the rate of intensity of loading is nothing but equals to ei into d4 y by dx4, which is equals to minus w. So with that you see one can easily obtain those conditions which are valid for either a simply supported beam with the UDL or what. So now you see here the last case which we want to discuss, that if we have a cantilever the simply supported beam, not UDL is there, a point load is there, but the point load is not exactly at the mid of the span of this particular beam, it is somewhere else. You see the eccentric loading is not eccentric, it is somewhere else, you see this kind of a loading is there. So again we would like to apply the direct integration method. If the expression is entire of beam is not valid for the total beam, that means you see whatever the expressions which are coming, it is not symmetrical, just like you see in the previous three cases we have seen that cut the x-axis and then go for the entire at x equals to 0 to x equal to L. So that part we discussed those things, but now here you see in this condition in which you can see on your screen that we have a simply supported beam, but the point load W is acting at the portion A. That means you see portion A and portion B are not equal. So you see here, for this we would like to calculate the deflection for this kind of beam where this kind of loading is there at distance A from the left end. So you can see here, first of all, we would like to calculate the reaction forces at these two extreme corner, and if I am saying that the reactions are R1 and R2 at these 2 points, and we have the point load at the point B. A and C are simply on the extreme corners and they are bearing these reaction forces on the top of direction, and in the some portion from the left hand side at A, we have it is this point B which is experiencing by this concentrated load W. So this is a complete configuration of this particular problem, and now you see if you want to find it out the bending moment for the portion AB, that means you see the begin portion, you see right from left to this portion where the W is there, MAB is nothing but equals to R1 into X for the reason 0 which is less than equals to X is less than equals to A. And now you see if you are going for the another portion, that is B to C, the bending moment is somewhat different, because you see here the both W is also putting some effort in that, because till now you see only the reaction forces are there, and due to that the bending moment is coming, that's why it is equals to R1 into X. And for the this BC portion, we have the bending moment is equals to R1 into X minus W into X minus A, because you see now the middle portion, this point load is there. So by keeping this remain, now we have this particular portion which is B to C is there, so W into X minus A, and this is valid for 0 which is less than equals to X is less than equals to L. So now you see you have bending moment for both of the reason. So now for we need to calculate again this deflection equations and the bending moment equations from those conditions. So for that, again we would like to go for the basic equation of the deflection. So we have the EI into dy by dx square, which is equals to R1x for AB portion, and EI into dy by dx square, which is equals to R1x minus W into X minus A for BC reason. So now you see you have the two different cases and the two different equations are there for the bending moment of these things. These two equations can be integrated in a usual way to finding out the deflection, but this will result in a 4 constant of the integration. Obviously you see in the first equation you have A and B, in another equation you have C and D. So again you see the 4 constant of integrations have to be evaluated for these things to calculate the deflection curve, and to evaluate the 4 constant the constants of the integration, 4 independent boundary conditions are to be there actually, which we always needed to be there at each support. So you see here for condition A or for condition B, one has to be realized that actually there are 4 different conditions, and for that we need 4 different boundary conditions for these cases. So which is not an easy task for this. Further, since the deflection curve is smooth, the deflection equation for this same slope and the same deflection at a point of application of load, that means at x equals to A, it has to be same. That means you see if you are talking about a smooth curve or a symmetric region, this deflection as well as the slope has to be having a constant value and they have to be same. Therefore, the 4 conditions required to evaluate these coefficients are to be derived one, and then you see we can simply go for these constant ones like that. You see at x equals to 0, that means the begin point, we have no deflection because it is a simply supported beam, so there is no deflection is there. But this is for portion A of B, that means you see for portion AB we have one boundary condition at x equals to 0, there is no deflection, so it is valid for 0 which is less than equals to x, which is less than equals to A portion. At x equals to L, now we are going in the BC region, y equals to 0, that means you see in the another region there is no deflection for the portion BC obviously, and which is A is less than equals to x is less than equals to L. The fourth condition is at x equals to A, where you see the point load is there, the dy by dx is same for both of the portion, because you see we are keeping one point load at this particular portion, so slope must be equal to for both of the portion, that means for AB and for BC the slope must be equal. And the final thing is that at x equals to A, the deflection is also same for both of the portion, that means you see by symmetricity one can be easily get you see the the slope as well as the deflection part for both of the region, and then it can be evaluated because both are equal in the both portion. So now you see here, first of all, since you see the reactions are there of one R1 and R R2, and since it is coming from both of the this supporting points due to this like the load condition. So R1 can be easily calculated by putting the moment equation and the force equation 0. So you see here, since because under the action of this load the beam is in the symmetrical way, that means it is in the constant way, so R1 can be easily calculated with that. So R1 is equals to WB by A plus B, and since you know the R1, so you see here for AB portion, means for the first portion, EI into dy by dx square is equals to WB by AB, that is this R1 into x is there, and for BC section, that means for the another section, we have EI d2y by dx square is WB by A plus B into x minus W into this x minus A. That means you see you need to simply replace this R1 which is equals to WB by A plus B. So now you see you have the two equations, integrate those things to calculate the slope. So we have the slope EI into dy by dx is nothing but equals to WB divided by 2 A plus B into x square plus k1. Now is we are taking k1 is a constant, and for k2 is the different constant for the slope for BC region. So EI into dy by dx for BC region is equals to WB by 2 A plus B x square minus W into x minus A whole square by 2 plus k2. So now you see here we have the two different constants k1 and k2, and now we would like to put like the conditions here, that like the boundary conditions to evaluate the other things. So for these things you see we have k1 and k2 which is equals to A if I am saying that this constant. So now like if you are keeping those things, what we have EI into dy by dx is equals to WB divided by 2 into A plus B x square plus k, because you see we are simply replacing those the constants. So we have k is like in place of k1 we have the k, and now for another reason, so this equation first, which is EI into dy by dx which is equals to WB by 2A plus B x square plus k is valid for AB region. Now for BC region again we can go for the slope condition EI into dy by dx which is equals to WB by 2A plus B x square minus W into x minus A whole square divided by 2 plus k. So now you see here you have like the two different conditions, and you have the two different equations, the differential equations are there, and now you see by integrating those things we can get the slope conditions for A portion and for B portion, because you see as we just got to know that actually if you apply the load at a particular position, the slope will be equal for both of the sections, the deflection is equal for both of the sections. So EI into y for AB portion, that means the this deflection condition is WB by this 6 A plus B into x cube plus kx plus k2. Now you see here we have the new term, that is k3 is there because of the integration term, and then for BC portion we have the slope condition EI into y which is equals to WB by 6 A plus B x cube plus this x cube is there, then minus W into x minus A whole cube divided by 6 plus kx plus k4. So now you see here we have the different conditions, and now if we use the condition which we have used for AB portion, this is AB portion for this one you see, and this is for BC portion, then you see like with the using those conditions in equation A, which we have put those things, we have k3 is equals to 0, and by keeping k3 is equals to 0 in this condition here, because like at the what will be the deflection at this reaction point is 0, as I told you that since it is the point load is there, so there is no deflection at the supporting reaction. So at x equals to 0 we have there is no deflection, so you see k3 will be 0, because if you are keeping x equals to 0, this x and this x will be gone and this y will be gone, so k3 is 0. So now we have the k3 is 0, so by keeping those things, what we have here in this equation, we have like the WB divided by 6 times of A plus B L cube minus W times of L minus B whole cube, this W minus A whole cube divided by 6 plus k times of L plus k4. So now you see here at x equals to initially we put at x equals to 0, y equals to 0. In the BC term we have x equals to L, y equals to 0. So by keeping those things, what we have k4 value, and this value is nothing but equals to minus WB divided by 6 times of A plus B L square plus W times of L minus A whole square divided by 6 minus k times of L. So now you see you have all the values of the constants, and now you see if we know that this total length of beam is L, which is divided into two portions A and B, so A plus B equals to L. So now by keeping here you see L minus A, so this A plus B equals to L, so L minus A will give you B. So here we can simply keep this B, and you see we have what we have k4 is equals to minus WB, this one, divided by 6 into A plus B whole square, because you see here L is nothing but equals to A plus B whole square. So it will be cutting out those things, plus W into this L minus A. So L minus A will be coming as you see B square. So you see here the B cube divided by 6 minus K times of A plus B. So what we have, you see this cubic term will be gone by one way. So we have WB A plus B whole square by 6 plus you see WB square by this 6 minus K into A plus B. So all these you see in this particular coefficient, all these terms are coming in terms of A and B. So we can simply segregate this beam into the different sections of A and B as compared to the total length. So now you see here this K3 can be easily find it out with the using of these conditions in the of those which we recently got. If we keep this K3 into the different equations, and then we can get the deflection which is same for both of the portion at x equals to 8. So now if we are keeping those conditions, what we have the deflection which is same for the equation 5, which is exactly deflection is same for the equation 6. That means for BC portion and for this AB portion we have the same deflection. So now by equating both of the this deflection term which we obtained in the previous section, you see WB by 6 A plus B into the x cube plus kx plus k3, which is equals to WB divided by 6 into A plus B into x cube minus WX minus A whole cube divided by 6 plus kx plus k4. So this deflection term is there for AB portion, this deflection term is there for BC portion. Now as per the this simplicity, we know that the deflection is same. So by equating those things, what we have k4 is equals to 0, or we can say that k4, if we are keeping those values there, then we have this is exactly equals to 0, WB plus A plus B whole square by 6 plus WB cube, which we have obtained recently previous case, by 6 minus K times of A plus B equals to 0. So we can get the value of K, because K4 previously we observed those things. From these equating we got that K4 0. So now you see here we can get the value by keeping those things equals to 0. We can get the value of K. The K is equals to minus WB into A plus B by 6 plus WB cube divided by 6 into A plus B. So now you see you have the constant value K, which we observed these things. So now you have all those values for the constants. By keeping those things, what we have, you have the different equations for the deflection term EI into Y, for this first section WB divided by 6 into A plus B x cube plus kx plus k3, and you see by keeping those values, what you have the final equation for AB portion, the deflection equation EI into Y, which is equals to WB x cube divided by 6 into A plus B minus WB into A plus B into x divided by 6 plus WB cube x divided by 6 into A plus B. So this is a valid equation. It is varying with the A and B, that actually how the different loading conditions are there for a BC portion and AB portion for this kind of reason. And similarly you see we can get for a BC portion EI into Y is equals to WB x cube divided by 6 into A plus B minus W into x minus A into whole cube divided by 6 minus WB into A plus B into x divided by 6 plus WB cube x into divided by this 6 times of A plus B. So this is for a BC portion. So now you see here we have a AB portion, we have a BC portion, and if we are keeping at x equals to A, we have the maximum the deflection term is there, and which is equals to W times of A square B square divided by 3 times of EI into A plus B. So you see here what we have a straight equation that if if we don't have exactly the this loading condition at the middle of the portion, then we can easily evaluate that the load conditions, and due to the load condition you see how the deflections are varying and the slopes are varying, we can easily get those values. So here we have the maximum deflection where the x equals to A, that means where the load application is there, and which is equals to this. So now if we are keeping that, if A and B are equal, that means if the load application is there exactly at the middle portion, that means at L by 2, then we have the WL cube by 48 EI, and which is the pretty simple case is there. So just keep in this keep in your mind that if we have a simply supported beam and the point load is acting, if this point load is acting at exactly at the middle portion, then we have the deflection, maximum deflection at the middle portion, which is equals to, and it is going in the downward direction, so minus sign is there, minus WL cube by 48 EI. And if it is not exactly this load is acting on the middle portion, if it is acting somewhere in this particular beam, let us say at A distance is there from this left hand side, as we discussed in the previous case. So we have the deflection at that point, maximum deflection, and that is equals to minus W A square B square divided by 3 times of EI into A plus B. So how these the variations are there, we could configure those things. So now we would like to conclude this chapter, that we started from the main deflection formula, that like if you know the bending moment m, then you can calculate 1 by ei into d2y by dx square. So with that, you see we configured that we can easily get the slope as well as the the bending moment, shear force and the rate of loading. And then we discussed the 4 different cases, in that the 2 cases were discussed for the cantilever beam, that if it is subjected by a point load and the UDL. And then you see the 2 different cases were discussed for the simply supported beam, that if it is the UDL is there, and if it is the point load is there but not exactly at the middle portion or somewhere else, then how we can get the deflection, what are the boundary condition which has to be taken, and then where we can get the maximum deflection as well as the maximum slope for these cases. So these you see of the 4 different cases which were very important and which are very practical, which have the very practical applications for this kind of the cases. So now you see in the next this chapter, we would like to discuss something about the alternate method, because you see sometimes you see here when there is an eccentric loading is there, then it is not in a simple method, the direct integration method. So what are the alternative methods are there for this kind of analysis first, and second you see we would like to analyze with the using of some examples. So in the next lecture we are going to discuss all those issues. Thank you.